Okay. Thanks for the reminder. I keep forgetting about it. So last time we did the Hamiltonian formulation of Lagrangian mechanics. So we derived Hamilton equations. We introduced Poisson brackets. And we have a definition of the integral of motion, or the integrals of motion. And then I started a short overview of symplectic geometry. So I introduced symplectic manifolds. So it's just a smooth manifold and a two-form on M such that the two-form is closed and it's non-degenerate. And the easiest way to think about it is if you write it in local coordinates as a two-form dxi which dxj, then the determinant of this matrix should not be zero. And then there are more sophisticated ways to do this. So then I introduced a very important notion of special submanifolds in any symplectic manifold. So this notion is the notion of isotropic submanifolds coisotropic submanifolds, and finally Lagrangian submanifolds. So these are all special submanifolds. I mean, you can characterize them in the following way. I'll just remind that it's if you have a submanifold M, N in our symplectic manifold M, then it has a tangent bundle. So to each tangent space, you have the orthogonal tangent space that is in the cotangent space to N. To M. So this is just a space of all linear functions that vanish on these tangent vectors. But also omega is a two-form. So contracting it with tangent vectors, you get a map from the tangent bundle to the cotangent bundle. This map is an isomorphism because omega is non-degenerate. So since N is a submanifold in M, omega gives a bundle map to T star M. And as a result, so we have this one, and we have omega of Tm as a subbundle in M. And it's our friend N is isotropic if omega Tn is in this conormal bundle to M. So this bundle is called with these fibers is called conormal to M. So that's the first notion. The second notion is N is coisotropic if This conormal bundle is a subbundle in omega Tn. And I don't think I had time to give examples. I think this is what I promised today. And this is what I will do today. And then the last notion is N is Lagrangian if it is both isotropic and coisotropic. And just last remark, the dimension of isotropic submanifold is always less than n. I assume that the dimension, so I assume that the dimension of M is 2n. The dimension of coisotropic submanifold is always greater or equal than n. And then it doesn't leave any room for the Lagrangian submanifold. It's a half-dimensional submanifold. And it's equal to the dimension of m over 2. And you know, this is a very nice property because for two generic Lagrangian submanifolds, let's say L1 and L2 in M, the intersection of L1 and L2 is a collection of finitely many points. Okay, so this is what happened last time. Any questions about the last time? Okay, so then let's do examples. Suppose that M is R to M with coordinates Pi and Qi. I keep some indices, lower indices, some indices, upper indices, having in mind that this is nothing but the cotangent bundle to Rn with coordinates Qi on Rn, and on fibers we have Pi as usual. So this, in this case, an example of an isotropic submanifold is, we can, for example, consider a k-dimensional submanifold where all q's are 0 and some of the p's are also 0. Clearly, the dimension is k, and in this case, p1, pk are global coordinates on such M. So this is a very simple, not very interesting geometrically example. So then the second example is more interesting. So let's consider cotangent bundle to Q, and let's assume that N is a submanifold in Q. So Q itself is a submanifold in T star Q via the mapping Q goes to 0 Q. This 0 is P equals 0. This is called a zero section submanifold. Why it's zero section? Because you have a natural projection from the cotangent bundle to Q itself. You just forget about P. So you pi of PQ is just Q. And you have a section S, that's this mapping. It is a section in a sense that composition of P and S is Q. It's the identity map. Okay, so now S induces an embedding N to Q to T star Q. Claim it's an isotropic submanifold. It's a nonlinear version of the first example. The first example is simply kind of a linear version of this one. Proof. That's a very nice homework. Okay. So another example, let's return to our flat case with coordinates pi and qi and with the symplectic form dpi dqi. It's the same symplectic form as in the first example. I just forgot to write it. So, and let's consider now n, which is determined by equations. All coordinates p starting from k plus 1 are 0. And now I think, yes, I misplaced indices. This should be upper indices. I want to be pedantic. Okay, and here it's fine. So the dimension of n is n plus k, and claim n is co-isotropic. So just a remark. You see, n is a submanifold, and we have omega on m. So if you have a form on the ambient manifold, you can pull back this form to n. So let omega n be the pullback of omega on n. Or kind of loosely I can say it's a restriction of omega to n. So how do we compute it? Well, we just, so by definition, it's sum over I dpi dqi. But now the sum is not to n, but to k. The coordinates that are conjugate to this momenta, they don't participate in this form. Well, you can compute it. So compute it using the definition. Homework.
Should that be omega n?
Omega n, yes. Sorry.
Thanks.
Thank you. So, so as you can see, if you take part of n with coordinates q1 through qk and p1 to pk, this will be symplectic. manifold. So we will return to this fact, and when we will briefly discuss the symplectic reduction. So this is coisotropic, and in fact, this pair n omega n, this is a presymplectic manifold. So last time I made the remark that if omega is closed, but if it's degenerate, this is called presymplectic manifold. So coisotropic submanifolds are examples of presymplectic manifolds. So another example is, again, it's a nonlinear version of this example. So let n be a submanifold. When I say submanifold, I mean closed submanifold. This is the embedding. So we already had this discussion of, I already used the notion of conormal bundle. It's a submanifold in our symplectic manifold claim. Conormal bundle to M in this symplectic manifold is a coisotropic submanifold. And again, proof. It's a nice homework. You know, you can prove this without going into local coordinates by definition of coisotropic submanifold that we had last time, and we had at the beginning of this lecture. The other way to do it is just use local coordinates and reduce it to the third example. So it's both ways work well here. So now let's continue discussing the cotangent bundle. So in this case, of course, M is the cotangent bundle to Q. So first, let's consider. Yep.
I'm just wondering if the inclusion as submanifold is around the right way.
Okay.
Because coisotropic means that n should be at least n dimensional.
No, right? No. It's this one is coisotropic.
Oh, okay. I misread it. Okay. Ah, right. Yeah. Okay. Yeah. I missed the conjugate. I mean, missed the yeah. All right. Thanks.
This one.
Yeah. Okay. That makes sense.
Oops, I was experimenting with my pens here, and I think this is too fat. Yeah, like this. This is better. Okay, so zero section. Q embedded to as a zero section. In other words, Q goes to a zero Q. Is a Lagrangian submanifold. It is both isotropic and coisotropic. So I'll just give these examples without the proof, but it's always good to prove these statements. So then that's the first example of Lagrangian submanifold. let's fix a point Q. So then at Q we have the cotangent space. At Q, obviously it's a subspace in the cotangent, in the total space of the cotangent model. And it is Lagrangian. And in both cases, one way to do it, so one way to prove this is local coordinates. Pi, Qi. So it's good in this case. Oh, wait, what did I do? Ah, I know. Okay. It's good in this case, and it's also good in this case. So C, another example. Let's choose a smooth function on Q, and let's choose not a zero section, but let's consider so our manifold is still T star Q in local coordinates. So let's suppose that Qi are local coordinates on Q, Pi are coordinates, global coordinates on T star Q in the basis. Oh, I'll write it loosely as ddqi. So this is the basis. This is something that you can identify with the basis in the cotangent space. Oh, sorry. No, wrong. Dual basis to what I was trying to write. That's a basis in T star Q. And the symplectic form is just dpi dqi. So this is our symplectic manifold. And now in this symplectic manifold, we consider NF defined as you take the differential, the RAM differential of F at the point Q, comma Q, where Q is in Q. In local coordinates, the RAM differential is df dqi Q, and then this basis dqi that I already mentioned. So it's clearly a submanifold. It is a section of our projection on Q. SF of Q is just what I wrote before. In the cotangent direction, you stick not 0s for the zero section, but the differential of this function. And claim it is a Lagrangian submanifold. And again, it's a homework. And again, you can either use local coordinates or you can do it in the invariant way. Both ways fine. It works both ways. So if you prefer coordinates, it's fine. If you prefer coordinate-free way, it's also fine. If you are an expert in partial differential equations, you probably will prefer coordinates. If you're an expert in kind of symplectic geometry, you probably prefer coordinate-free way, but they're equivalent. So remark, f equals 0 is the zero section. In this case, n0 is just q. Q embedded in T star Q as a zero section. Okay, so do we have other examples? Yes, we do. D. Oh, no, it's actually, so this is all about cotangent bundle. So now let's look again at some other example of symplectic manifold. Let's consider the M to be a sphere of radius R in R3. So just defined by this equation. I already mentioned that if epsilon ijk is a totally antisymmetric tensor, then this form is actually symplectic. This is, I mean, the reason for this, there is a sophisticated reason for this. It's just that if you say that R3 is the dual space to the Lie algebra SO3, then S2 becomes a coadjoint orbit. And it's a standard fact that if you have a Lie algebra, its dual space will have something that's called Poisson structure. Let's not discuss it yet. But the important fact is that every coadjoint orbit that is not too singular is a symplectic manifold. Orbit. And if it's singular, then on smooth parts, it still has a symplectic structure. Coadjoint orbit is a symplectic manifold. And in terms of Poisson geometry, you see G star is a Poisson manifold, and these coadjoint orbits are so-called symplectic leaves of the Poisson, of this Poisson structure. I'm not going to write this because we will discuss it later, but actually probably not in this course. So so when I say omega, what I meant is, so this two form is a two form on R3, and you kind of, if this is the embedding, then you pull back this two form on S2, and that's symplectic on S2. Okay, so then I gave the definition, and then any curve C in S2 is a Lagrangian submanifold. Let's say any simple curve so that it wouldn't have self-intersections, and it wouldn't have any singularities. So it means no self-intersections. Okay. So we had isotropic, coisotropic, Lagrangian submanifolds, and we had some examples of all of them. So any questions about this material? I'm going to briefly explain what is the symplectic reduction, and then we'll return to Hamiltonian mechanics.
For the dual space example, I mean, for the Lie dual algebra example, what is the symplectic form?
Okay. So G is a Lie algebra. Let's choose a basis. Now, I love local coordinates. Is a basis, and xi are coordinates in this basis.
Mm-hmm.
So actually, sorry, I don't need those. I will need coordinates on G star. So once I choose coordinates, the Lie bracket gives these structural constants.
Mm-hmm.
So G star has a dual basis. Dual to the basis that we choose for G. And let xi be coordinates on G star in this basis. So then let me try to write it. So let's consider omega. Omega is a two form on G now, on G star. So it's sum CKIJ xk dxi dxj, sum over I, j, k. So you see now, oh no, sorry. Something is wrong. No, I'm trying to cheat, and it's never a good idea. so I should introduce the correct object, and that's a Poisson bivector field. C Kij xk, and then sorry, ddxi ddxj. Okay, I'll give a definition, and then we'll return to this very, very soon, and it will be more clear. So it's a bivector field. P is a section of the exterior square of the tangent bundle on, in this case, it's G star. But it's degenerate in the sense that P as a mapping from the cotangent bundle, just the contraction of covectors and vectors. So the tangent bundle has a kernel. The claim is that if you restrict P to the to any coadjoint orbit, is non-degenerate, and it gives an isomorphism between tangent bundle and the cotangent bundle, and that means the inverse mapping is a symplectic form. I know you did I answer your question?
Yes,
Okay.
thanks.
So I don't think there is a better way to construct it.
Right, thanks.
Anyway, any other questions? So then let's do symplectic reduction. So, you know, it's supposed to be an hour and a half, right? So we started at 7:20, so we go to 8:50. Let's just say this will be the standard time. So symplectic reduction. Suppose we have a coisotropic submanifold. So so we have a form. We have the symplectic form omega on n. We have the pullback to n. That's a two form on n. This is m. And this two form on n gives a mapping from the tangent bundle to n to the cotangent bundle to n. It's just a collection of kind of continuous collection of mappings between tangent spaces and cotangent spaces. And it's just a contraction of a form of cotangent vectors and tangent vectors. So, but now this map has a kernel. This map was an isomorphism. Sorry. So this map was an isomorphism. So yeah, it has a kernel. And the kernel of this, so it's a subspace in the tangent space to M. And in fact, this is a, so when you fix, for each x, when you fix a tangent, a subspace in the tangent space, and if these subspaces form a vector bundle, so that's called a distribution, a tangent distribution. On M, and then it's an integrable distribution in a sense that, in a Frobenius sense. So, so for each
I
x,
just wanted to check. The contraction map should it be using omega instead of omega n, or I mean maybe it doesn't make much of a difference, but
so sorry, what did you say?
yeah, should the omega n be omega? Is what I'm asking.
I think it doesn't matter actually.
Okay.
Oh yeah, it's actually. Wait, sorry.
I mean, we're thinking of tangent space inside.
You know,
of
I think I'm kind of, yeah. Actually,
okay.
it should be like this. And it should be like this.
Okay.
Yes, so late hours. So we have tangent distribution on n. That's what we will be using. It's an integrable distribution. So it means that for each x in n, there exists, I don't know, Lx submanifolds in n such that tangent space to this submanifold Lx is the kernel of TXM. And this Lx is called a leaf of the distribution. So so the definition and underscore is the space of leaves of this tangent distribution. So we would do the following. We sort of taking quotient with respect to this tangent distribution. That's the idea of passing from a manifold with tangent distribution to the space of leaves. So it's okay, and typically it's rather singular. Nobody said that it's a manifold. It can be rather far away from a manifold. But if n bar is a manifold, it inherits a symplectic structure omega n bar. From this pre-symplectic structure omega n. So this procedure is called the symplectic reduction. It's also, I mean, it's, yeah, I guess in terms of functions, the Poisson brackets on n bar corresponding to omega n bar is the Dirac bracket Dirac introduced Poisson brackets on constrained phase spaces. So basically, this is some kind of geometric version of what Dirac did. Okay, so here's an example. So here we have two examples. And why did I mention this procedure? It's just because symplectic manifolds, the ones that we know so far, they are cotangent bundles to submanifolds in the configuration space. So remember that I say why we care about Lagrangian mechanics on manifolds, because we can constrain the dynamics in Rn to a submanifold in some ambient Rn. So in some sense, this is a step further. It's when we do constraint in such a way that we constrain not only coordinates, but also momenta. So this way we can obtain rather complicated symplectic manifolds. And the symplectic reduction is one of the machines that produce these more complicated symplectic manifolds. The other machine is symplectic leaves in Poisson manifolds, but this will bring us quite far away from quantum mechanics. So let's move on to quantum mechanics. And first example is when m is R to n. So with the standard symplectic form, meaning that this R to n is just a cotangent bundle to Rn. Let's say that n is exactly the one that we considered before. As an example, we consider the submanifold where all momenta starting from k plus 1 are 0. And then the result of the reduction is just the manifold with the coordinates p1, pk, q1, qk, and the corresponding symplectic form is the one that was degenerate on n. It's this one. So this is one example. It's very natural. So, and the other example is, let's consider m to be the cotangent bundle to q with the symplectic form given by the same formula, but now in local coordinates. And let's say that m is a submanifold in Q. Then the conormal bundle is a submanifold in the cotangent bundle, and it's coisotropic. And so the question is, what is the result? Cool. what is the result of the symplectic reduction here? Does anyone have some guesses what it should be? What is the most natural symplectic manifold that you can associate to any manifold? You have a smooth manifold, so how can you construct a symplectic manifold out of it?
Tangent.
Cotangent bundle, yes. So that's another nice homework. And that's the end of the symplectic reduction. And I just realized that I forgot to mention a very, very important fact about symplectic manifolds. So any questions about the symplectic reduction? So the reason why it's here is just I wanted to introduce it as a tool to construct more complicated examples of symplectic manifolds, though we didn't see they are more complicated in these two examples. Okay, so then let's move on. So very important remark, Darboux coordinates. So it's the following theorem that on any symplectic manifold, there exists a system of local coordinates such that, well, okay, so I'll be a little bit more detailed so that this is the coordinate neighborhood, and on U alpha we have coordinates P alpha I, Q alpha I. So omega on U alpha, so claim that there exist such coordinates that omega has this form. And if you change coordinates to another coordinate chart, in the new coordinate chart, it will still have this form. So these are Darboux coordinates. Proof. There is a book by Arnold. It's called Mathematical Methods of Classical Mechanics. So, for example, you can look there. Or any textbook or review on symplectic geometry. It's a very basic fact. Now, Darboux coordinates, symplectic manifolds are rather flexible in the sense that these coordinates look like canonical coordinates, but in fact, there are infinitely many choices of Darboux coordinates. So they are not unique. I think that's all I wanted to say about Darboux coordinates. What's important is that they always exist. So locally, any symplectic manifold looks like Rn with the standard symplectic structures. Locally, it looks like a cotangent bundle. So they also called Darboux coordinates. Sometimes, especially in physics, they called canonical coordinates. They are not canonical in the sense that they are not unique, but they are canonical in the sense that the symplectic form has this very special way in this, has this very special form in these coordinates. Okay. So, any questions? So if there are no questions, then let's discuss the Hamiltonian mechanics on general symplectic manifolds. So suppose that we have a symplectic manifold, smooth function. So then H defines the vector field. So what is the vector field? So vector field attaches to every point x a tangent vector to M. And it does it in the following way. VH is equal to P DH, where this is the Derham. So DH is just sum over I from 1 to M, DH dxi dxi, so 2M. Xi are local coordinates. And P is a mapping from the cotangent bundle to M to the tangent bundle to M, which is the inverse to omega mapping tangent to cotangent. So naturally P is a bivector field. And when you do the mapping from the cotangent bundle to the tangent bundle, you pair the bivector to a covector. The remaining part is a vector. Okay. And in local coordinates, it means the following. So in local coordinates, we have di, which is d dxi. It's a basis in tangent spaces. dxi, it's the dual basis in the cotangent space. And omega, if you write it in terms of this basis, the form, so it's omega ijx dxi dxj, and then px, if you write it in terms of coordinates, it's this di dj, where omega ij is the inverse matrix to omega with low indices. Delta ik. So this is, yeah, and then once you have this, then omega ij is just simply some, so sorry, then this vector field is some omega ijx, sum over ij, dh, dxi, dj. Okay. So this is where we started. That's the invariant definition of the Hamiltonian vector field generated by H. This is the name of V. So then invariantly, P is just the inverse map to the isomorphism between the tangent bundle and the cotangent bundle that's given by the symplectic structure. And in local coordinates, we have these two dual bases on the tangent and the cotangent bundle. Any two form has this form. Any two vector has this form, but in our particular case, this is the symplectic form, and this one is the Poisson tensor. So it's a Poisson bivector field. We already had the notion of a Poisson bracket. So on R to N. So we will have it now on any symplectic manifold. And now in local coordinates, our vector field, Hamiltonian vector field, can be written in this way. And so we have two kind of, yes, so I want to introduce the components of this vector field. So then flow lines. So then definition, trajectories of the Hamiltonian dynamical system generated by H are flow lines of this vector field VH. In other words, solutions to differential equations dxt dt is equal to VH xt, or in coordinates dxit dt is equal to Vi xt. Okay, so this defines dynamical system, and Hamiltonian mechanics on symplectic manifolds that's the study of this dynamical system, study of solutions to these differential equations. So now one more thing. Poisson bracket on smooth functions on M. So if we have two functions, f1, f2, c infinity m, the Poisson bracket is defined as the contraction of the two vector field by vector field and the two form, which is df1, df2. Or in local coordinates, this is simply sum over ij, omega ijx, df1 dxi, df2 dxj. Okay. Any questions so far? Okay, theory. I shouldn't say this. This algebra of smooth functions with this bracket is a Poisson algebra. In the sense that this bracket satisfies, let's say that's the first property, the Jacobi identity. And second, if you have three functions, then the bracket of f1 with, so in other words, this bracket acts by derivations on the commutative algebra structure. Proof. Again, it's a nice exercise. First property, the Jacobi identity, follows from the closeness of the symplectic form. And the second property is obvious. Obvious because in each of the functions f1 and f2, the bracket has only first derivatives. So this is simply the Leibniz rule for the derivatives. I mentioned Leibniz, and I just, I cannot resist but to say, the Academy of Sciences in Russia was established in early 18th century. And actually it was Leibniz who personally convinced Peter the Great to establish the Academy of Science. And before this, in 1700, at the turn of the century, the Prussian Academy, the famous Prussian Academy of Sciences, was established. And that was also the result of persuasion of Leibniz on Frederick the Great. So he was a very interesting man. Okay, so so that's the Poisson bracket. And what else I didn't say? Ah, yes. So classical observables. So functions on the phase space, that's by definition are classical observables. There is nothing else. There is nothing to say. But you see, one can introduce a natural notion of the evolution on classical observables. So we have a dynamical system. So given H, we have the Hamiltonian dynamical system. M with trajectories xt. So we can define the evolution of classical observables ft of x is equal to, by definition, x of t, where x of t is trajectory, is the trajectory that originates at x. The assumption is that t is sufficiently small so that there is a unique trajectory that originates at the point x. So for large t, there could be singularities, but we consider the evolution for small, sufficiently small t's. So that's the evolution of classical observables. And then the theorem that describes this evolution is the following. The derivative of this evolution in time is equal to the Hamiltonian Poisson bracket with the function itself. So this is the linear. So that's the theorem. Proof. Let's prove it in local coordinates. So df dt x, by definition, it's d dt f of x of t. We use the chain rule, my favorite trick. dxi f xt. But then we know that it's a Hamiltonian vector field, so this is equal to omega ij xt dh dxj xt df dxi, it's this one, xt. So it's equal to h f ht ft, but htx is equal to h of x. We already discussed it with last time. It's just simply if you use the same the same logic, so then you will get HT, which is 0. That implies that H is constant, and so this proves this theorem. And it's actually very, it's a kind of important philosophical statement. So you see, when we consider the equation for the, this is the equation for xt. We have finitely many equations. We have n equations, 2n equations, for 2n unknowns, first order nonlinear differential equations. So what do we have here? In this differential equation, we have infinitely many unknowns. Let's suppose we have, I mean, we don't have any good basis in the space of C infinity functions, but suppose that we are in some algebraic setting where, say, we can replace C infinity by polynomials. In polynomials, we have a polynomial basis. So then we can say that there are infinitely many unknowns. These are the coordinates of this polynomial basis. And infinitely many equations. But these equations are linear. So the kind of dichotomy between the evolution of observables and the dynamical system itself is that we linearized this nonlinear, finitely many nonlinear differential equations. We linearize them at the price that we have infinitely many equations and infinitely many unknowns. And you know, some people say that quantum mechanics is easier than classical mechanics because it's about linear differential equations. So you can say the same about classical mechanics. If you consider the evolution of observables, again, you have the linear differential equations, you linearized everything, but sort of at the same price that you pay in quantum mechanics for linear differential equations. Linear differential equations, these are operators in infinite dimensional spaces, and these two phenomena are of the same nature. Okay, so so this is the evolution of observables. And what else? Yes. So, so kind of conclusion. Space of observables, classical observables. We'll pass the quantum observables soon. Space of classical observables is the space of smooth functions on the phase space. It's a Poisson algebra. Mathematical structure on it is natural structure is a Poisson algebra. And the evolution defined by, generated by H, maybe better to say, is this linear differential equations. So these are equations of motion, the way how they evolve. And the initial condition is f0x is f of x. That's the initial condition. If we would know how to solve infinitely many equations for infinitely many unknowns, we wouldn't go into the kind of nonlinear ODEs defining the dynamics. We would just be solving this system of linear equations. Okay, so it's almost time to stop. So I think I will not start the new subject now. So next subject is variational principle for Hamiltonian dynamics on a symplectic manifold, so-called Hamilton-Jacobi principle. But it's a big subject, so we'll do it next time. And then when we will analyze variational boundary conditions, we will see that Lagrangian submanifolds, they play a really essential role in variational boundary conditions. And we will discuss boundary conditions and what should be understood by boundary conditions in great details. Okay, any questions? Any comments?
Yeah, so here's sort of like a philosophical question. When people ask, when people say that they're trying to understand, for example, Hamiltonian dynamics, I'm guessing that this means, okay, they first specify Hamiltonian, and then, and then, like, what about the classical observables do they want to understand?
Well, usually when people, I mean, if you see someone and someone will tell you that he or she, they work in Hamiltonian dynamics, it's by definition, it means that they are solving these nonlinear ODEs that come from the Hamiltonian evolution.
Okay.
So you see, Hamiltonian dynamics is very special because it's generated by the Hamiltonian.
Mm-hmm.
So VH is generated by the Hamiltonian. And as a consequence, H is constant on trajectories. So you can reduce your dynamics to level surfaces of H from two n-dimensional manifolds to n-1 dimensional manifold. And then there is also a very simple criterion for integrals of motion. You may have another function, f, such that its bracket with h is 0. If you found such function, then you can reduce the dynamics to even smaller submanifold, to level surfaces of h, joint level surface of h and f.
Okay, wait. So I'm still trying to understand. Let's say that okay, I work with the less general context where, okay, I'm restricting myself to a level set of H. So for them, they're like saying, okay, we want to solve dft dt equals to some constant times ft, basically. Is that the idea?
No, this is completely hopeless.
Okay.
It's a useful tool to say, for example, if you know that this bracket is 0, then you know that f is preserved. Then you know that the dynamics goes along the level surfaces of
Mhm.
F and H.
Mhm.
Then you can restrict to these level surfaces and try to solve the differential equation there.
Okay. But
And
where
you
are the
see,
differential equations coming from?
the differential equations, these are the
Oh,
level, sorry.
those. Okay. Okay.
Mhm.
The
That's
level
the
curves of
Hamiltonian
the actual
equation.
Hamiltonian. I see. I
Mhm.
see. Okay. 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 That makes a lot more sense now. Okay.
So
I see.
somehow the beauty of the Hamiltonian dynamics is that you have a guaranteed integral,
Mhm.
H itself.
Right. Right.
But
So you're
then
already simplifying the system substantially.
a little bit, not
Okay.
substantial, but a little bit.
It's one dimension. That's
Well, it's just a little.
okay.
So then, actually, there is a nice notion, since we discussed it, complete
Okay.
integrability, completely integrable system.
So I'm guessing you're gonna say you find enough H's, I mean enough F's so that um, they they're independent and they match up to the dimension of
Exactly,
okay.
exactly. It's when you have, I mean, I'm oversimplifying a little bit, but if you have n independent, let me call this IN just. Independent Poisson commuting independent simply means that if you take the this n form, it never vanishes. I mean, it's not identically zero. It can vanish at special points, but it's not identically zero. The Poisson bracket is zero, and so then there are many nice features. I can tell about it later, but not sure if now is a good time. Actually, I can say about it now. So then, let's say MC is a level surface of those integrals. And there is a theorem attributed to Liouville. He certainly did something about it, but some people say that actually it was done by someone else, but it doesn't matter. So it's called Liouville theorem, which says the following, that xt goes along this level surface. It's completely clear because the Poisson commute with the Hamiltonian, so all the trajectories, they belong to these level surfaces. And what is a little bit less trivial is that on MC, yes. So MC is always isomorphic to the product of a copy of Euclidean space and an n minus k dimensional torus. In particular, when MC is compact, it's isomorphic to n minus k. And then there exists an affine coordinate system on MC. Affine coordinate system means that coordinate transformations is a combination of linear transformations plus translations. Such that in these coordinates, let's call them x alpha, the dynamics is linear. It's V alpha that depends on the Hamiltonian on C, T plus x alpha 0. So topologically, and geometrically, it's very simple dynamics in this case. And amazing fact is there are plenty of such systems. So this is one of my favorite subjects. Classical and quantum integrable systems. So these are classical Hamiltonian integrable systems.
What is K here? Or what did that?
It depends. It's some number from 0 to n. It's a sort of the degree of non-compactness. If k equals 0, oh, I'm sorry. If it's compact, then it's just n. If k equals 0, then there is no Euclidean part. You have compact level surface. And in fact, it's again, it's not a difficult theorem. It's basically because the Hamiltonian dynamics of all other integrals, it gives you the action of the abelian group with n generators. And then topologically, every manifold where this abelian group acts transitively, it's always isomorphic to one of those. If it's totally non-compact, then it's arc n. If it's totally compact, it's S1 to the n, it's a torus. And there are cases when it's sort of in between.
And is there any general saying like what kind of system is integrable and what not?
That's the statement. If you have such functions, then it's integrable. Of course, if you start with specific Hamiltonian system, it's very difficult to say whether it's integrable or not. It's always a miracle if it turns out to be integrable.
Okay.
Like one of the most remarkable examples is this Korteweg-de Vries equation. It's a partial differential equation, which is I'm sure I'm writing something wrong. Something like this. It's a nonlinear PDE. And it's an integrable, it's an infinite dimensional integrable system. So that's, I mean, it was a remarkable discovery by, you know, there were some stages. Gardner, Green, Kruskal, Muir, they discovered certain technology how to solve it. So then Lux found that it's a Hamiltonian system. And then Fadeev and Zakharov, they understood that it's an integrable system. And constructed all the Hamiltonians.
Thanks.
Okay. Any more questions?
Yeah, for the KDV hierarchy, what is the Hamiltonian and what is the manifold? Is that hard to say, or?
The manifold is it's the space of, well, the space of functions ux, and then you choose various conditions on these functions to make it sort of more meaningful. The Poisson bracket, the symplectic structure is something like this. It's a double integral du x du y, I think dx dy. You integrate from minus infinity to x over dy, and then over dx you integrate from minus to plus infinity, something like this. So I can give you some references, but it's there are many such systems now.
Yeah,
It's quite remarkable. This goes back to 1970s, early 1970s.
Okay, thanks.
Okay. Any other questions?
Well,
Is there?
okay.
Yeah, go ahead.
Okay, I have a kind of philosophical question about, is there any difference between integrable systems and exactly solvable modulus systems?
Exactly solvable is like, it's like a gambling. You can solve it, you can not solve it. So it's there is no underlying concept. It's just you either solve the equation or you didn't solve the equation. Integrability, it's a structure. It's a mathematical structure. So one can, I will return to this next time, and we will see what it means. It's actually, since you already know what Lagrangian submanifold is, so I will explain more precisely what means a completely integrable system. It's not necessarily a dynamical system. It's a certain structure on the manifold. It's a Lagrangian vibration on the manifold. And the Hamiltonian, the dynamics is completely integrable if the trajectories, they go along the fibers of this vibration. So you see, it's actually, there is a very rich structure. But if you have an ordinary differential equation which you manage to solve, I mean, you solved an engineering problem. So you found a solution to a differential equation that could be very useful, but there is no mathematical structure here. So normally, say when people say solvable systems, typically it means integrable systems. It just, in many cases, especially in the physics community, the terminology is somewhat loose, and but that's what usually people mean.
Okay, thanks.
Another little question. Is there why isotropic is called isotropic? Like, how should I memorize which one is included in which for isotropic?
It's very simple. If you have a form omega on some vector space V, let's say W in V is, so omega is V tensor V to, say, C, or to O, doesn't matter, is isotropic for omega if omega UV is 0 for any U V in W. It just, if you restrict it to omega, it's identically to W, it's identically 0. That's what it means, isotropic for any form on V.
Okay, thank you.
Uh-huh.
Okay.
Okay.
If no one has other comments, I have a comment for this morning class. I think at some point you said you would have like an expert for recording. No, you didn't get it?
So
Like
what,
in the morning. I'm talking about TQFT,
yes, yes, yes. So
the recording. I thought at some point you said you would get like a official team for the recording. No?
I think it was recorded.
Yes, it is recorded. It's not very clear at some point.
Really?
Um, it's almost like it need a little bit of focus, so it's not focusing well.
Okay, so I didn't know this, so I'll complain about
Okay,
this.
yeah, please do it.
Oh, wait. Do you mean on the Zoom video or on the uploaded video?
On the Zoom, I haven't checked the uploaded yet,
Ah,
and I'm not the only one complained. Some other guy complained last time, but yeah. So anyway,
Because I'm not sure how the system's set up, because right now they have like a big camera at the back. So maybe that's not going to Zoom, that they're just recording that and then they're going to process that and then upload that.
okay, I see.
Did you check the recordings? Because they definitely should. I
Um,
mean, they definitely do something sophisticated.
okay, I'll check the recording.
Yeah,
Okay,
maybe the
I'll
live
check.
broadcast is unclear, but maybe the recording's better.
Okay, that'll be. I'll check it out.
Okay, I'll check this too.
All right.
Okay. Okay, guys. So then I'll see you next Tuesday.
I did have one more question, but it's actually not for you. It's for Daniel. Because
Well, okay.
yeah, you mentioned Estonia before, and I'm guessing you guys were based at the Euler Institute. Is that correct?
What?
Were you guys previously based at the Euler Institute?
No, I'm from St. Petersburg State University. I'm bachelor student.
Oh, okay,
not a-
okay, my mistake. I was
It's
gonna
okay.
ask if you knew someone, but okay, never mind. All right.
No,
I know some people who are postdocs there.
Okay.
Whom do you know?
I mean, she's not a postdoc. She was a student at the Euler Institute. A girl called Paulina, I think. But I don't know what her last name is. She went to Estonia to study instead of maths. Anyways, not important. I just. Okay.
Yeah, I'll check. My co-author, she was a postdoc at Euler, so she may, I think she knows everyone there.
Okay.
Okay.
All right. Thanks.
Okay. Good night.
Have a
Bye-bye,
good night.
everyone.
Bye bye. See you.
Thank you. Bye.
Okay. Bye.
Thanks.
Thank you.
Welcome.